Let us look at classification of organic compounds. Organic compounds can be classified in two ways. The first way is on the basis of structure, and the second is on the basis of functional group. Structure and functional group. So let us first see the classification based on structure. Organic compounds can be classified into aliphatic compounds and cyclic or closed chain compounds. Aliphatic compounds are those compounds which are open chain. So aliphatic compounds are open chain, and we have cyclic, which are ring compounds. Cyclic compounds can further be classified into homocyclic compounds and heterocyclic compounds. Homocyclic compounds are those compounds in which the ring is made up of only one kind of carbon atom, whereas heterocyclic compounds are those compounds in which the ring is made up of more than one a carbon atom as well as another atom like nitrogen, oxygen, sulfur, etc. So homocyclic compounds can further be classified into homocyclic, alicyclic compounds and homocyclic aromatic compounds. Heterocyclic compounds can also further be classified into hetero-alicyclic and hetero-aromatic compounds. Let us look at examples of each of these compounds. An aliphatic compound is an open chain compound. A simple example would be N-butane. N-butane, it is a straight chain compound and an open compound. Cyclic compounds can be homocyclic as well as heterocyclic. In homocyclic, we have alicyclic compounds. Alicyclic compounds are those compounds which are ring compounds because there is the word cyclic, but they have only carbon atoms and single bonded carbon atoms. So an example of an alicyclic compound is cyclopropane. It is a three-membered ring in which there are only carbon atoms bonded to each other by single bonds. Homocyclic aromatic compounds are those which contain only carbon atoms but they have alternate single and double bonds. An example is benzene. Another example would be aniline. and so on. Heterocyclic compounds. As the word suggests, hetero meaning different. Hence, these compounds consist of more than one different atom. For example, in a homocyclic compound, there are only carbon atoms. In a heterocyclic compound, there can be carbon and nitrogen or sulfur or oxygen. Again, heterocyclic, alicyclic compounds are those compounds which are single bonded. Heteroalicyclic compounds. Hetero again meaning a heteroatom like oxygen, nitrogen, carbon, etc. Since it is alicyclic, there will only be single bonds. So I can have a compound this compound is called tetrahydrofuran or THF. It is a heterocyclic alicyclic compound because it consists of a heteroatom which is oxygen and there are only single bonds. A heteroaromatic compound would be a compound in which there are alternate single and double bonds and a heteroatom present. So I have a heteroatom. This example is pyridine. Now, aromatic compounds are further classified into benzenoid and non-benzenoid compounds. So let us first look at aromatic compounds which are homocyclic. So aromatic homocyclic compounds can further be classified into benzenoid and non-benzenoid. Benzenoid, as you can see from the word itself, it has benzene in it, and hence these compounds resemble a benzene nucleus. This is benzene. So any compound which consists of a benzene nucleus is called a benzenoid aromatic compound. A simple example is aniline. In which there is a benzenoid nucleus and hence it is a benzenoid aromatic compound. A non-benzenoid aromatic compound, non-benzenoid means there is no benzene. An example is tropone. In which this does not resemble a benzene nucleus and hence it is a non-benzenoid homocyclic aromatic compound. Aromatic heterocyclic compounds can again be classified into benzenoid and non-benzenoid. Again, benzenoid means resembling a benzene nucleus, but here, since it is heterocyclic, there will be the presence of a heteroatom. So an example here would be quinol. There is a benzene nucleus and hence it is a benzenoid compound. It is aromatic and heterocyclic because of the presence of N, which is a heteroatom. A non-benzenoid heterocyclic compound would be azocine. It is heterocyclic because it has the presence of a heteroatom, but it does not resemble a benzene nucleus, and hence it is non-benzenoid heterocyclic aromatic compound. Now let us look at classification based on functional group. We have different functional groups. Alkanes are generally represented by C single bond C. And the general representation is RH. Alkenes have a C double bond C. Alkynes have a C triple bond C. Alkyl cyanides have a functional group C triple bond N. Nitroalkanes have an NO2 group. Alcohols have an OH group. Phenols are AROH, that is an aromatic ring and an OH group. Aldehydes are C double bond OH. Ketones C double bond O. Carboxylic acids C double bond O OH. Ethers have an ROR group. Esters are C double bond O OR. A functional group is nothing but an atom or a group of atoms in an organic molecule which determines its characteristic chemical properties. So either an atom or a group of atoms giving this particular class of compounds a specific chemical property is called a functional group. Let us now look at electron displacements in a covalent bond. The first effect that we're going to look at is inductive effect. Let us consider the molecule ethyl chloride. Ethyl chloride is a polar molecule as there is a high difference in electronegativity between chlorine and carbon. Hence, it is a polar molecule. It is polarized in such a way that carbon number 1 gains some positive charge. I can write this as plus delta. Delta means a very small positive charge. This is carbon 1. This is carbon 2. And the chlorine atom gains some negative charge. This is due to the high electronegativity of chlorine. The shift of electron density shows that the arrow points from plus delta to minus delta, which means that electrons are being pulled towards chlorine. C1 has developed a positive charge. Hence, it in turn draws some electron density from its adjacent neighbor. Consequently, some positive charge develops on carbon 2 because carbon 1 is pulling some electron density from carbon 2. Hence, carbon 2 develops a partial positive charge. This partial positive charge is smaller than delta plus delta because it is further away from chlorine. Such a polarization of a sigma bond caused by polarization of the adjacent sigma bond is referred to as inductive effect. I repeat, a polarization of a sigma bond, this is my sigma bond, due to polarization of the adjacent sigma bond is referred to as inductive effect. Inductive effect is a permanent effect. This effect is passed on to the subsequent bonds but the effect decreases as the chain length increases. I have another example. Butyl chloride, in which due to the electronegativity of chlorine, it pulls electrons towards itself. It develops a partial negative charge, as well as carbon 1 develops a partial positive charge. In turn, carbon 1 pulls electron density from carbon 2, and hence carbon 2 develops a partial positive charge which is less than the positive charge of carbon 1, and this effect goes on down the chain. As you can see, the charge of carbon 1 is greater than that of 2, is greater than that of 3, and 3 is greater than that of 4, which means that the inductive effect decreases along the length of the chain. There are two kinds of inductive effect. Minus I effect, in which electrons are pulled by the groups which show minus I effect. Groups which show minus I effect are highly electronegative atoms like fluorine, chlorine, bromine. Hence, even in our example, chlorine is the one which shows minus I effect because it pulls electrons to itself. Plus I effect means losing electrons, and that is seen in highly electropositive atoms like CH3, C2H5. In this case, CH2 is losing its electrons or giving its electrons to chlorine, and hence it shows plus I effect, whereas chlorine shows minus I effect. Let us look at our second effect, which is electromeric effect.